So today we'll finish up talking about linear momentum. It's worthwhile looking closely at what we do today based on what I just said. Um, and we'll also talk about rotational momentum at the tail end. Um, the interest in rotational momentum, this is the simplest example of something related to rotational momentum and explains it kind of quite nicely in terms of what we'll do. So if we're looking at linear momentum or rotational momentum, you could imagine that this is the form in which we do lots of work, useful work. So hydroelectric dams, for instance. Don't know if the dams that are breaking in the Carolinas right now are hydroelectric dams or just water control dams. I don't need that particularly. We'll do this. We'll see if they... Okay, yeah, that's actually a perfect figure. And so turbines are one way to be able to convert energy from kinetic energy and linear kinetic energy, straight line, the stuff coming down from the dam into this turbine, into rotational kinetic energy, which can then be transferred into electricity by running a stator through a magnetic field, creates electricity through Faraday's law. And so that is a typical way in which we use conservation of momentum, linear into rotational and rotational into electricity to be able to do something moderately useful for society. And so my reason for mentioning that is that you can imagine that this rotor that you have the dog chasing around, you could view it in two modes. You could clamp it and you could hold it in your hand and it would squirt out and you'd feel the torque of it trying to turn in your hand. And there'd be no work done there because work is force, which you have, a torque, times a velocity, but there's no velocity. Or you could allow it to free spin and attach no force to it at all. And in that case, there'd also be no work because there would be no force, but there would be a velocity. Now, power, so work is force times distance. Power is force times velocity, as we know. So if you're not holding it, there's no force, but there's a velocity. So there's part of that equation which is missing. And so we'll look at that in terms of the things that we can do both in terms of linear momentum and in terms of rotational momentum because it defines how we do work. Okay, so that's our task for today. Hopefully this isn't all playing in the background and overprinting my... this is kind of cool as well, since it's already half running. This is the opposite, right? This is putting work into something. Very clever, I think. Looks like something you could deploy in... actually, the work is being done by the river flowing past it, and it just fills this pipe up with water, and it's basically a big, long Archimedes screw that allows it to be pumped into somewhere else. Very, very, very clever. And obviously no power input except the power of the water flowing past it. Okay? So let me make sure that I'm going to kill this so we don't have to deal with this. And I'm going to come back to work on this. So we're interested in... Let's see, let me do this. Sometimes it's useful to look at this. If just to confirm exactly what we've talked about before. So this is maybe worthwhile starting here. And so let's talk about linear momentum first. We've already started dealing with that. This equation is always valid. We can rewrite this if we wanted to, and we have rewritten this, just to recap, as the velocity of flow relative to a control volume plus the velocity of a control volume, let's say, could be a control surface, but we won't look at deforming control volumes, times mass flow rate equals sum of forces. We know that these are vectors which have components in x, y, and z, but usually we resolve things in one direction. And if we resolve things in one direction, it would be just the relative velocity in the x direction, say, plus the velocity of the control volume or control surface in the x direction times the mass flow rate equals the applied force in the x direction, all of them. And so that's one fundamental relationship we can work with. The second one is that we talked about relative frames of reference. And the key was that the velocity of the fluid relative to the static is equal to the velocity relative to the moving coordinate frame plus the velocity of the control volume, I guess. So this here, this expression here, really comes from the substitution of v static in there. That's all. And so that expression is always going to be valid for the things we'll do in this class, always. Absolutely, those two expressions. And so we can figure out how we might use them in a variety of different ways. Yes? Can you speak up, please? Oh, it's blurry? Is it blurrier than usual? I don't know what to do about that. I can make it bigger. Maybe that will make it sharper. Is that better? Okay. All right. No problem. Good. All right. So this, of course, relates to what we've talked about. We often did it with the New York Fire Department boat. This is W. This is the velocity of the control volume. And this is relative to a viewer who's looking. Can I do an eye? This is what an eye usually looks like, right? Who's looking at this. So the velocity relative to the static reference frame. And so this will always be true. We will always look only at steady state problems. And so the ramifications of steady state would be that sum of the mass flow rates is equal to 0. And we'll also look at non-deforming. In other words, the balloon isn't getting smaller as it puts out air. In other words, it's a control volume that doesn't change. We'll mainly be looking at steady state and non-deforming. And if we're looking at non-deforming ones, then what we will find is that since this is a constant always, right? This isn't deforming, but it's moving at some velocity. So put any number in here that you want, some velocity in the x direction. If the sum of the masses, mass flow rates, always sums to 0, then the product of these two components have to cancel out. Then for the case where it's steady and non-deforming, so in other words, V control surface is equal to V control volume, right? If the ship is getting cramped, then clearly all of the parts of the control volume are not moving at the same velocity. And so this would not be true. But if it's not deforming, then they would be true. In that case, we can take this relationship and we can write it as this, but with this term cancelled out to 0, because the product, the sum of these components, this sum has to equal 0, because sum of mass flow rates equals 0. So, but the bottom line is you can always use this expression and this will start cancelling out. So that's the first point to make about conservation momentum. The second point to make is that we can choose two modes of behavior. Two n-member modes. And a series of modes between those. One is we could call clamped, for want of a better word. And so clamped means that we're applying a force to keep it static. And so by definition, the velocity of the control volume is equal to 0. And so in those cases, we'd like to know what is the force that we have to apply it to keep it in place. So sprinkler idea, you clamp it, there's a force, it's trying to turn against you, but it's not moving. Control volume is static, but you have to apply force to do that, or in a linear case. The second case would be moving. And so the velocity of the control volume is not equal to 0, but force is equal to 0. So you let it do its thing, it goes wherever it goes, and you solve for the velocity. So in one case, we solve for the forces that are applied. The other case, we solve for the velocities that it reaches. And you could imagine that in between these, we could have a prescribed velocity of the control volume, in which case we would want to calculate, well, we'd know the velocities, but we'd want to calculate what the forces would be to do that. So, but these are the two n-member modes, and it's useful to think about that. So I thought today we might do a couple of very straightforward examples to be able to make that case. And they rely, I'm going to shoot this down momentarily, they rely on this basic idea here of having a vein, V-A-N-E, not V-E-I-N. You have water coming in at some flow velocity, it strikes this vein, it shoots up here, and you could ask those same two questions. You could ask the question, if I hold this here with some force in the x direction, so it's static, then what is the magnitude of this force? Very first case. Or if this force is equal to 0, what is the velocity this vein will move at? And so those are the two cases we can look at. And you'll see that we use basically this expression down the bottom is basically W plus V CV m dot equals sum of forces. Sum of forces is here. We're only interested in doing it in one direction. This term here is m dot, mass flow rate. And we've said that if it's not moving or if it's steady state, we can get rid of this term and it just disappears. And we're left with this term here. And so let's explain that in due course. So the expressions that you need, will need, and we do need today, are this, and to understand it, and these relative velocities as well. But we'll reiterate that today. I'm just going to go through some self-worked examples in case that's not so clear. All right? So if this is blurry, we'll make this big enough so people can see. And this is the idea. Okay. So what do I want to deal with? All right. So the first is, I say on my notes anchored, but we'll call it clamped. So this is linear momentum. Oops, let's take it nice and easy. So this is A. So clamped. So in other words, the velocity of the control volume is equal to 0. What is the force in the x direction? Here's the geometry of this idealized vane. I'm just going to do it at 90 degrees just because it's easy. You have a velocity coming in at point 1. You have a velocity going out at point 2. Is that big enough? Should I write bigger? It's still blurry? Okay, all right. We know that this is point 2. We know that this would have an area 2. We know that this would have an area 1. We know that it has a velocity of the control volume, which in this case we're going to put equal to 0. And we're going to do the calculation for it to be able to figure out what's going on. Okay. What's the equation that we need to use? It's relative velocity at point 1 plus the velocity of the control surface at point 1, all in the x direction, mass flow rate at 1, plus the relative velocity at point 2, plus the velocity of the control surface at 2, mass flow rate at 2 is equal to, if we draw the coordinate system, x and z. We don't really care too much about z. And force in the x direction. You can imagine that the force you have to apply to react against this to keep it static is going to be in the opposite direction of that. But this is definitely our positive direction, right? And so it'll turn out to be negative if it should be negative. That's the only force we have applied. What do we know? We know that let's make life easy in that we can imagine that A1 is equal to A2. We could rationalize that based on conservation of volume, right? Conservation of mass, because we have this. This isn't a tube. This is a free spinning jet that's on our vane, and so we would know that the velocities v1 and v2 are equivalent to each other. What else would we know? We know that we're holding this static. So this is 0. We know also that these are relative velocities in the x direction because we're resolving in the x direction. Because we want to know what the force is in that direction. So we can look at what those magnitudes might be. What else do we know? We know that this here must be equal to, what's this? This is V1 times rho times A1. This is V1 times rho, sorry, this is V2 times rho times A2. But we also know that from conservation of mass, M1 plus M2 must equal to 0. And so if that's the case, then these are equal to the negative of each other. So we certainly know that as well. So what we could do is we could look at these individual components. What else do we know about this? This is the velocity in the x direction as it comes out of here. The velocity in the y direction is certainly something, it's v2, but the velocity in the x direction has to be 0. So this is the velocity in the x direction at this point. So this has to equal 0 as well. And so we're left with an expression which is, if we write it out in longhand, I guess the only term we have left is W1 mass flow rate 1 is equal to the force in the x direction. Let's look at the appropriate signs for this. This is in the coordinate direction, so this is actually the same as V1, because we know that if I write it out that V1 is equal to W1 plus velocity of the control surface at 1, and this by definition is 0, we've said. So this has to be the case. And this is V1 density A1. Sign convention, this is positive in the positive x direction. Sign convention, flow in is negative, right? So Fx, force in the x direction, is just going to be equal to minus V1 squared density times A1. Velocity is a positive number here, so squared minus. So the force in the x direction is not towards your right, but it's towards the left. It's a reaction holding it in place, right? So that's the more straightforward one to do. And probably I took a long time to do it, just a bit convoluted, but this is ultimately the expression that gives you the force that you'd have to apply with the correct sign attached to it. All right? Okay. All right. So, same problem. I'll let you, if people are writing that down, all right. So the second, same problem, but now unclamped. So by definition, force in the x direction is 0. What is the velocity of the control volume? Same geometry. I'll draw it again down here just so we have it. V1, V2, Fx equals 0. Velocity of the control volume not equal to 0. So that's the question. The question is, what is the velocity of this control volume, if we want to figure it out. So the expression we have is no different from this, except we perhaps can't throw away all of those components. So let me write it here with the same thing here. W1 plus velocity of the control volume and control surface are the same things, times the mass flow rate at 1, plus W2 plus velocity of the control volume at 2 multiplied by mass flow rate at 2 is equal to sum of forces in the x direction, and we can figure out what's going on. We're resolving in x again, so I guess we can talk about this. So each of these are relative to the x direction. and let's see what we can start throwing away. We've said we're not clamping it, we're allowing it to move. So by definition, this is equal to 0. Okay. We're going to define that it's a steady problem. Steady state means that the sum of mass flow rates are equal to 0. Physically, a better way of saying it perhaps is that there's nothing accumulating in here. The mass rate of flow in here is the same as the mass rate of flow out here, so you don't start accumulating fluid in this on this vein. And if that's the case, as a consequence of this, what we said is that the velocity of the control volume times the mass flow rate must also sum to 0, because this is just a constant that we're multiplying it by. So if that's the case, we can get rid of these two. Not because individually they're 0, but because together they are. Okay? So we're still working with the idea of being able to do that. I'm going to move this up so I can do this. So what do we have left? Well, we have left that the relative velocity W1 in the x direction, mass flow rate 1, plus relative velocity at point 2, again in the x direction, times mass flow rate 2 has to equal 0. What else do we know? We know that mass, so from this, we know, for instance, that the mass flow rate 1 is equal to minus the mass flow rate 2. So if, for instance, we substitute this into here, then I'll write it down here, then we have W1x times minus m2 dot plus W2x times m2 dot equals 0. And so we can get rid of both of these because they cancel. And we have that W1x is equal to W2x. So what does that mean if we look at this? We don't really know what this is, but we could rewrite this, for instance, if we zoom up to the top of the page, where it isn't written, okay? By definition, V static equals the velocity coming out of the front of the hose on the boat plus the velocity of the control volume. These could be in the x direction. So this is the velocity we see the water going at if we stand by the Statue of Liberty. This is the velocity of the boat, and this is the velocity the guy firing the hose sees it coming out of the hose at. So what we could do is we could rearrange this so that we write it in terms of this, which is just Wx is equal to the velocity static minus the velocity of the control surface. This we can also write in the same way. So we can write this expression as V1 static minus velocity of the control surface is equal to, so this one is this term here, is equal to V2 static minus velocity of the control surface. Just by using this. We can cross out each of these because they exist on both sides. This is the velocity in the x direction. And so if we look at this boat here, this is the water that's coming out of here, which is coming out at V2, but this is V2y, and the water has a velocity V2 in the x direction. What velocity is the x direction? Well, if it's moving with the control surface, then these two, by definition, have to be the same. So this is the velocity of the control surface at point 2, which is the velocity of control surface anywhere. And we know what V1 static is because that's the velocity of the hose that comes in here. So the bottom line is that the velocity of the control surface is equal to the velocity 1 of the hose. So the big picture. So dial yourself out of what we've done in this kind of minutia. Big picture, you hold the vane static, you get the maximum force on that vane, but the velocity by definition has to be 0, but you can calculate the magnitude of that force. The second end of the spectrum, and so this is this, if we go back to here, this is the point that we made here. This is the clamp case which we did here. We set the velocity equal to 0, we calculate the force that you have to apply. The other end of the spectrum, completely release it, allow it to move, no force is applied, and we can figure out, we can attempt to figure out the velocity of the control surface. In this particular case, and actually in most cases, if you look in the past exams, we do an example with the decapitated cylinder. The velocity, the steady velocity of that cylinder is the same as the velocity of the fluid that comes out of the back. That's the maximum velocity it can attain. Likewise, in this particular case, the maximum velocity that this can attain is going to be given by the velocity of the incoming hose. And that makes sense, really, because if you think about it, if I'm the vane, the hose is hitting me in the front, the only way I can make that hose not apply any force to me is to be running backwards at the same velocity as the hose. Yeah.
Are we always supposed to assume it's steady state, or is that just given the problem?
The only cases, it would be probably given the problem. So this expression with the W plus VCS is always true. The VCS term will drop out if it's steady state. The one case where it's not steady state is the gas cylinder one. And you know that because you have a gas cylinder, you have one nozzle, so fluid is net exiting it, and so the pressure inside it has to be depleting as it does that, and so it's not steady state. But in this case it is. Yeah, good question. Okay? So, which brings me to the non-steady state case. Thanks for the segue. All right, so you saw it earlier on today. So non-steady state. So a bit convoluted on this last one, but I think it's useful to look at the things we talked about. You can interpret that in any way you so wish. All right. This is my sleeping giant, the gas cylinder. X and Z. And the other point is that the forces that we're talking about are the forces that are required to clamp it in place. In other words, I would call it the reaction. And so it's the force you have to apply to be able to keep it from moving. Force in the x direction, velocity of the control volume, because it's not deforming. You'll never be asked to do one for deforming control surface. It's just too complicated. There's a velocity v1 and the mass flow rate m1 coming out of here, which is going to be equal just to the velocity v1 times the density times the area. And I think numerically we'll do an example. Let's call m1 equals 1 kilogram per second, and v1 is equal to 1 meter a second. Okay. So let's do it the same as we did before. For variety, let's call it anchored. Which is also clamped. So what does that mean in our interpretation? It means that velocity of the control volume is equal to 0. If we write out our conservation of momentum expression, it's the velocity coming out of the relative velocity to the structure at point 1 in the x direction, plus the velocity of the control volume at point 1 multiplied by the mass flow rate at point 1 is equal to the force in the x direction, or sum of the forces. We know that it's clamped, so we know that this is 0. We know the mass flow rate, because I just told you that it's 1 kilogram per second. It's out, so it's positive. So in other words, it would be V1. Well, that's not complicated. I'm giving you a mass flow rate. Mass flow rate obviously would be equal to V1 density A1. But I'm assuming that we just have that. The flow rate relative to our system here is equal to 1 meter per second. It's flowing in this direction, so it's negative. And so the force would be minus 1 meter per second times 1 kilogram per second equals the force in the x direction. And we know that minus 1 kilogram meter per second squared is just equal to minus 1 Newton, right? By definition. Newton's the force required to give 1 kilogram an acceleration of 1 meter per second squared. And so the force to hold it in place is minus 1. So in other words, we have to apply 1 Newton in this direction to stop it going anywhere. All right. The complementary component is unclamped, I guess. And we use the same expression. So what do we know? So I guess the complementary would be that the force in the x is not equal to 0. And so clamped, by definition, the velocity in the control volume is not equal to 0, but the force in the x direction would be equal to 0. So it's the complementary condition for this, if you like. And we have the same equation. So we just have to figure out what the components are. Velocity 1 in the x direction plus the velocity of the control surface, again in the x direction, mass flow rate at point 1 has to equal sum of the forces in x. We've said this is 0 by definition. If that's the case, then we know that because these have to sum to 0 individually, that W1x has to equal negative velocity of the control volume. And the only way that that can make the case is that if this is minus 1 meter per second, then this ends up being the velocity of the control volume is equal to plus 1 meter per second. So this is the velocity that it's coming out of here at, and this is this magnitude here. And so, again, just as in the case, we made the point when we had the vane that was hitting the target, so the only way that it could physically not provide a force to that target was for this target to move back as quickly as it was coming, and it was going at the same velocity as the flowing fluid. In this particular case, this is the velocity relative to the control surface. We don't have to do any manipulations. You remember last time we said that the static velocity is the relative to the vane velocity is equal to the static velocity plus V control volume, and we rearranged it to take this over to the other side, so we had this, and then we could substitute in this. We don't need to do that in this case. We've said we have this decapitated bottle. We've said that we know the velocity that's coming out of it, and I guess that's the difference here, is that, actually I didn't do this very well. This isn't really V1, is it? This is W1, by our own definition. This is the velocity that it's coming out of this relative to the bottle, just by our definition. It comes out at 1 meter a second. And so with that, we end up with this magnitude here. And so it's not a surprise that in the steady state, in a perfect world, when there's no friction that's holding this back, friction would act on the base of this as it scoots across here. It would act against its moving, in this case here. Then in that case, the velocity it goes at is actually the velocity of the jet that comes out of it. So get a feel for what these components would be. And so just to bring this to closure, and just use this example. So you notice here two things. In one case, in the clamped case, we've calculated a force that is applied to this, and it's going at no velocity of the control volume is equal to 0. The other case, we've calculated the velocity, and the force in the x direction is equal to 0. The two end-member cases. If we said that the gas bottle is traveling at some velocity and we prescribed that, we'd probably calculate a force that's in between these and the velocity that would be in between these. The velocity can't be larger than the jet force. That makes sense. And the reason I mention that is that you could imagine making a diagram that looks like this, where you put on one axis the force, F sub x, and on the other axis the velocity of the control volume. We have 2 points, 2 cases. We have the case where it's clamped and we can calculate what the force is. Ignore the fact that this is negative, it's just a direction. And so if we have 1 Newton here and 0 velocity, then this exactly is this case. The other case, we have a velocity of 1 meter per second and 0 force. We have another point. We know that work is equal to force times displacement. We know that power equals work per unit time, which is equal to force times velocity. So in other words, the product of these two. We know these two end members. So this is the static bottle. This is the flying bottle. And if we allowed it to go at some intermediate velocity, maybe we would get a relationship that looked like this. We have a magnitude of force at this halfway point. So this is a half Newton. This is a meter per second. And so what we could do is we could plot power with velocity. And power we said is equal to force times velocity. So this point here, a force of 1 Newton times a velocity of 0 is 0. This point here, a force of 0 but times 1 meter a second is also 0. But a force of half a Newton, I'm just going to draw this, a force of 1/2 Newton times 1/2 meter per second is equal to 1/4 Newton meters per second. Newton meter is a joule per second. A joule per second is a watt. And so hopefully that reinforces the idea that to do work you have to resist against something. And so it's not good enough that it flies, that it's clamped in place and can't move. It can't do any work because it doesn't have any velocity to it. It's no good that you completely release it and have no force applied to it, because even if it's traveling, because it also doesn't do any work. So at some intermediate point, I don't know if it looks like this, but I think it would probably look something like this, is that you'd end up with some maximum amount of work. Okay? So, I will not have time to talk about rotational equilibrium. That might tell you something about what you need to work on for your test. I think there's still a question in the assignments for this portion that relates to rotational equilibrium, but you can do that.